This tutorial is going to be about drawing Lewis structures. First, I will explain the Lewis structure rules. Then I will go over some guidelines for how to connect the atoms. And then finally, we'll go over 3 examples. We'll draw some Lewis structures together, and I'll show you 2 methods for drawing them. And if you'd like a PDF of this presentation, you can go to my website, chemistrysky.com. Lewis structures are 2-dimensional diagrams of molecules. And remember, molecules are particles that are made up of atoms held together by covalent bonds. And molecules have 3-dimensional structure. But the Lewis structures are only 2-dimensional, so they're only showing how the atoms are connected and where the electrons are. And notice bonds are represented, show shared electrons, and unshared electrons are represented as lone pairs. The Lewis structure rules are as follows. The first rule is that the total number of electrons has to equal the sum of all the valence electrons. That is, you can't use more electrons than you have. Valence electrons, remember, include both s and p electrons in the outermost shell or principal energy level, and also include any charge. If it's negative, there are more electrons, and positive, you remove electrons. The second important rule is the octet rule. All atoms end up with 8 electrons, or 4 pairs of electrons, all electrons being paired in the diagram, and with the important exception of hydrogen, which ends up with 2 electrons, or 1 bond. In the Lewis structure, a single line represents a single bond, or 2 shared electrons. A double line represents a double bond, or 4 shared electrons. A triple line would be a triple bond, which is relatively rare, and representing 6 shared electrons. And notice bonds are all shared electrons. So bonds count towards, and count in the sense of when you're counting for the octet rule, the bonds count towards the octets of both atoms they're connected to, meaning they're more efficient ways of using electrons. 2 dots, which represent a lone pair, are 2 unshared electrons. So in terms of the octet rule, these only count towards 1 octet of the atom that they're on. So they're less efficient ways of using electrons. So these are the Lewis guidelines for connecting atoms. Hydrogen in group 1 has a valence of 1, so it always has 1 bond. And I'm just going to draw the electron dot diagram for hydrogen. Hydrogen has 1 dot, 1 electron, and so it can only form 1 bond. The halogens have 7 valence electrons in group 17. So I'm going to draw the electron dot diagram for chlorine, for example. Well, when you draw it, you put 1 electron per side before you double them up. This would be the electron dot diagram for chlorine. And notice towards an octet, it already has 7 electrons, so it only needs 1 more. So typically the halogens are only going to need 1 bond, and both the hydrogen and the chlorine, since they form 1 bond, are generally going to be on the outside of your diagram. They're not going to be the middle atom. And I say usually because there are exceptions, which I will talk about later. For example, in polyatomic ions, then the halogen is going to be in the middle. If your atom is oxygen, sulfur, or selenium in group 16 with a valence of 6, they're generally going to want to form 2 bonds, and I'll give you an example here. So we'll draw sulfur with 6 electrons, 1 per side, and then you start doubling them up. So notice with 6 electrons, they only need 2 more. So they're generally going to form 2 bonds. And again, that's just a usually. Nitrogen and phosphorus in group 15 or 5A have a valence of 5, so we'll give them 5 valence electrons, which means 1 pair and 3 single bonds. So they really need 3 more electrons to have an octet, so they're generally going to form 3 bonds. And carbon with a valence, and silicon in group 14 or 4A with a valence of 4 only has 4 valence electrons. So notice it needs 4 more electrons to have an octet, so it's going to always, and that's going to be another always, forms 4 bonds. And notice that means since nitrogen usually wants 3 and carbon always wants 4 bonds, they're going to generally be in the middle of your diagram. Okay, so those are the guidelines. With one, now slide has some additional guidelines. There's a rule which I call the uh-oh rule, because if you draw two O's connected to each other, you say, uh-oh, it's wrong. The exception being peroxides. An OO bond is a peroxide bond. So what that means is when you're drawing polyatomic ions or something like SO2, the O's are on the outside and they're never bonded to each other. So when you draw them bonded together, you say, uh-oh, it's wrong. Okay. And the other important guideline is to use pencil, because you're going to want to be able to erase as we move electrons around. The first example we're going to do is CHCl3 chloroform. So first, the connect the dots method. For the connect the dots method, we're going to just draw each of the atoms with their electron dot diagrams. Carbon has a valence of 4, and notice we're showing those 4 electrons, one on each side. The hydrogen we'll put on top with its 1 electron, and then we'll arrange the chlorines around the carbon, and we'll give each of them their valence of 7. 1, 2, 3, 4. And notice, let's put the lone pairs on the side that's not facing the carbon. So the chlorine on the bottom, 1, 2, 3, 4. And then we'll pair up the electrons not facing the carbon. Chlorine 1, 2, 3, 4. And then pair up the one. And then notice, then we can connect the dots. So in that bond on the left, it's made up of 2 shared electrons, one from the carbon, one from the chlorine. The top is sharing between the carbon and the hydrogen, and then we'll just connect all our dots, and that would be your final Lewis structure diagram. And it has the correct number of electrons because we used the valences when we were drawing the atoms. Now for the second method, which is just slightly different, we're going to just draw it. So carbon in the middle. Remember, we said carbon always goes in the middle, so we'll put everything around the carbon. We'll put the chlorines all around. And then octets, give every atom its octet. So notice the hydrogen has 1 bond, so it's finished. The carbon has 4 bonds, or 8 electrons, so it's got an octet. And since each of the chlorines only has 1 bond, that means they only have 2 electrons. We have to give each of the chlorines 6 more, or 3 more pairs. Remember, in the final diagram, all electrons are paired. So we'll give each of the chlorines 3 more pairs of electrons, and so then they have an octet. Now, when you do that method, it's very important in the end to count to make sure your diagram has the correct number of electrons, because remember, we just added dots to give everybody an octet. So we have to add up all the valences. So the hydrogen has a valence of 1, the carbon a valence of 4, and we have 3 chlorines, each with a valence of 7, and that adds up to 26 electrons. And this picture, in fact, does have 26 electrons, so that means it's correct. Okay, so now we're going to do another example. We're going to draw a simple polyatomic ion hydroxide. So for the connect the dots method, first we have our O, which has 6 valence electrons. So we're going to draw the 6 electrons. Okay, and then next to it we're going to put the hydrogen, which has 1 valence electron. And then we can connect the dots. But notice the hydroxide is negative. That means it has the diagram has 1 additional electron, and clearly the oxygen needs it, so we'll put that there. And that's how we get it from connect the dots. The draw octets and count method, we'll just say we'll draw O, we'll put an H in, give the oxygen an octet, and then make sure our picture is right by adding up all the valences. Oxygen has a valence of 6. The hydrogen added 1 electron plus 1 more from the negative charge. Our diagram can have 8 electrons, which it does. So that's correct. Okay, now we're going to do another example. Okay, our final example is going to be nitrate. Okay. So with the connect the dots method, we start with a nitrogen in the middle, give it electron dot diagram. It's got 5 valence electrons. We have each of our oxygens, which have 6 electrons, which means 2 lone pairs. And notice we'll put the lone pairs away from the nitrogen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Now when we draw our lines, you'll notice that the nitrogen has an octet, but nobody else does. But we still have one more electron from the negative charge on the nitrate, so we'll put that electron on the oxygen on the left, and we'll label this as negative. Now, we still have a problem because we have unpaired electrons, and our two oxygens don't have octets. So now is when the erasing comes in. So we're going to erase one of the electrons on top of the nitrogen and one of the electrons on the oxygen on the right. And we're going to then move the electron from the nitrogen down there, the oxygen electron there, and then notice we can have a nice double bond there. And now the oxygen on the right has an octet. The nitrogen in the middle has one extra electron, and so we can erase it. And in fact, the oxygen on the bottom needs it, so we'll erase that and put it on the oxygen on the bottom. And then we've got our Lewis structure. All the atoms have an octet. We've just rearranged the electrons, and this does resonate. It doesn't matter which oxygen you draw with a double bond. It could be any of them. They're equivalent. Okay. With the draw octet count method, we have nitrogen in the middle. We'll add our oxygens around it because we know the oxygens don't go next to each other because of the O rule. And now let's give every atom an octet. Notice the nitrogen has 3 bonds, so it needs 2 more electrons. Each of the oxygens has 1 bond, so they each need 6 more electrons or 3 lone pairs. And so what's correct about this structure that I've just drawn is that it satisfies the octet rule, but unfortunately has the wrong number of electrons. And we'll discover that by counting how many valence electrons we have. The nitrogen contributes 5. Each of the oxygens contributes 6. And we have a negative charge, so that's 1, and that adds up to 24 electrons. This picture has 26 electrons, and so that means we've used 2 electrons too many. Remember, lone pairs are less efficient than bonds, so that difference of 2 electrons means we need 1 additional bond. So what we must do is we must erase 4 electrons, and we're going to put back 2. Erase 4 electrons and put back 2. Right here. And then now the picture has 24 electrons. Okay, and that's it. I hope you found this helpful.